So section 4.2 deals with applications of linear equations. So these are essentially word problems. So in the previous section, we gave you the equations already set up. We had to maybe do a little rearranging and then solve. Now you're going to actually have to build the equations from the description in the word problem, and then you'll use the matrix algebra system to solve the equations. So we clean our house, and we find 1,036 coins totaling $18.52 in loose change. If you only find quarters and pennies, how many of each type of coin did you have? So we're going to assign variables. So we're going to say Q is going to be quarters, and P is going to represent pennies. So the first piece of information that I was told is that I have 1,036 coins. So I have however many pennies I have plus however many quarters I have needs to add up to 1,036. Then we're told that the amount of money that I found was $18.52. So if I take the number of pennies that I have and I multiply it by 0.01, it'll tell me how many cents I have, right? And I take the number of quarters that I had and multiply it by 0.25, we know that this adds up to 1852. So the key thing you have to remember when you're doing system of equations is whatever the value P is in this equation, it's got to be the same value here. So they have to have the exact same meaning. So this is how you calculate how much money you have, right? You just take the number of each coin, multiply it by its value, and you get the dollar amount. Here we just said, well, how many of each do we have? And it adds up. So P represents number of pennies. Q represents number of quarters in both equations. Now my coefficient matrix, as I'm just going to read my coefficients. So it's 1.01, 1.25. My variable matrix is PQ, and my coefficient matrix, B, is 1036, 1852. So our solution, C, should be a 2-by-1 matrix. So let's go back to our calculator. I'm going to go second matrix, edit, and I'm going to make this a 2-by-2 matrix. And so we have 1, 1, 0.01, 0.25. Now I'm going to go second matrix, edit. Matrix B is a 2-by-1 matrix. So it's 1,036, $18.52. So now I quit, second matrix, grab A, invert it, second matrix, grab B, and multiply, and we see we had 1,002 pennies and 34 quarters. So if we want to express this in words, we found 1,002, pennies and 34 quarters. All right, let's look at another one. So you have your bake sale for charity was very successful this year. On day 1, you sold 56 chocolate chip cookies, 30 muffins, and 23 slices of cake. On day 2, you sold 23 chocolate chip cookies, 61 muffins, and 42 slices of cake. On day 3, you sold 75 chocolate chip cookies, 16 muffins, and 76 slices of cake. And your revenue totals were $231, $355, and $482. So what price did you charge for each item? So since we know the number of items we sold, if we multiply that by the price, that gives us the total amount of money that we made off that item. So we got to assign variables. So we're going to let X be the price of the cookies, Y is the price of the muffins, and Z is the price of the cake. So the first day we sold 56 chocolate chip cookies, 30 muffins, and 23 pieces of cake, and our revenue total was $231. On day 2, we sold 23 cookies, 61 muffins, and 42 slices of cake, and we made $355. The third day, we sold 75 chocolate chip cookies, 16 muffins, and 75 slices of cake, and we made $482. So that means our coefficient matrix A is going to be a 3 by 3, and it's 56, 23, 75, 30, 61, 16, 23, 42, 75. Our variable matrix is X, Y, and Z. And our constant matrix is going to be 231, 355, and 482. So now I can go back to second matrix, edit. Matrix A needs to be a 3 by 3, and it's 56, 30, 23, 23, 61, 42, 75, 16, 75. Then second matrix, edit. B is now a 3 by 1 matrix, and we get 231, 355, 482, and so now I quit. Oops, quit, there we go. Second matrix, grab matrix A, invert it, second matrix, grab B, and when we multiply, we get 1, 2, and 5. So this means that cookies cost $1 each, muffins were $2 each, and each slice of cake was $5 each.